Okay, so let us proceed with the Timoshenko beam theory, a lecture in the honor of the renowned mechanician Timoshenko. Let me review what we did last time. We are talking about an approximate solution of problems of the beam geometry. And we have already solved this problem analytically, which is supposed to be a very good approximation to the, let's say, exact solution under appropriate circumstances. But a beam solution is, in a sense, let's say, something that we desire to have if it is applicable, because a beam is a one-dimensional theory. And versus an analytical approximation or a numerical solution of the exact three-dimensional geometry, a one-dimensional approximation is numerically, for instance, a lot more efficient. So if you have a structure that could be approximated as a combination of many, many beams, and you'd like to somehow analyze that in a numerical fashion, you want to get a very good structural or mechanical estimate of what is going on, the numerical solution will be much more efficient if you can use a beam approximation piecewise, okay, throughout the structure, for instance. So that's why we are interested in sort of gaining an understanding of what happens with these or within these approximate theories. And how does the analytical solution help us? Well, it helps us develop these theories because we know the features of the analytical solution, and we're trying to replicate those features in our approximate beam theory. So that's why the analytical solution is important, and that's why also the approximate beam theories are useful. So let me review what we have done so far. So we have two beam theories. And you can directly continue pretty much from where we left last time. Both beam theories sort of admit the following solution approach. Okay, so this way we are also reviewing what we did last time. So we are given a beam structure, and it is somehow loaded. And the loading can come in various ways. There can be a distributed load along the length of the beam. There can be a localized shear force along the beam, at the end of the beam, etc. And likewise, there can be a bending moment along the length of the beam. And so that's our loading. And given this loading, our goal is to determine what the deflection is. And deflection is something that represents the center line, the neutral axis, vertical displacement in the two directions, therefore. So, and we are interested specifically about deflection because I know what the stresses are like from the analytical solution. So given the load, I can always post-process and find what the stresses are. I am particularly presently interested in finding what the deflection is. And that's where the beam theories differ from each other, and that's where the analytical solution also differs from the approximate theories. So the first step towards this goal is to find what the rotation is. Okay. First step is the rotation step. And this step is the same for both the classical beam theory, which we learned in ME231, Euler-Bernoulli, as well as for the Timoshenko beam theory that we're talking about since last time. Okay, so the rotation is the same for both. And the way we work is we start from the third derivative. So derivative, remember, it's with respect to x1, the horizontal position. Third derivative of the rotation. And we know that the third derivative of the rotation is the distributed load divided by Young's modulus times moment of inertia. And we integrate that towards the second derivative. And statically, I know that V prime is equal to W, and therefore when I integrate, I will get this equality theta double prime is V over EI. And then I can integrate towards the first derivative, which I know will be m over EI, which you can finally integrate towards the rotation as a function of the lateral position x1. Okay, so this is the rotation of the cross-section. So these results, remember, are based on statics. So the lower set of equations, they are from statics. They've got nothing to do with any sort of deformation. But the fact that each of these equalities holds has to do with the approximation or the assumption that plane sections remain plane. And that assumption is common to both Euler-Bernoulli and the Timoshenko beam theories. So we are combining statics with plane sections remain plane assumption in order to develop this solution diagram in the first step for the rotation. So now, once we find the rotation, then eventually our goal is to find a deflection. And so we go to the second step, which is the deflection step. And this is where the two beam theories differ from each other. So we want to go from theta towards V. So that's the deflection step. And when we talk about the Euler-Bernoulli beam theory, the Euler-Bernoulli beam theory proposes the following. Well, I want to go from theta to V. So if I have an expression for V prime equals actually theta, then I can integrate towards V, and I'm done. Okay? So the assumption here is that plane sections remain plane after deformation, but not only that, they remain perpendicular to the neutral axis after deformation. And that's how we propose that V prime is equal to theta. Okay? Now, the Timoshenko beam theory, on the other hand, notices the following. Well, so this is equivalent to saying that we are omitting the influence of transverse shear stresses on deformation. That is not entirely correct. If the height of the beam is not very, very small, for sure it will cause some influence on the vertical deformation. So I need to somehow account for that. And we account for that in an approximate manner by assuming that the shear stress is, or the shear strain is approximately constant along the height of the beam, which of course is not true. But if we make that assumption, we obtain that V prime is not equal to the rotation of the cross-section, but rather there is a difference that has to do with the fact that the slope changes also due to the presence of the shear stress. Now, if we just put assume a constant shear stress, this is the assumption, this is the result that we got. But then we also argue that, well, in reality, the transverse shear stress distribution is not a constant. I know that from the exact solution. So why don't I put here some constant that will account for the fact that it's not a constant, perhaps by adjusting this value k, which we call the shear correction factor. Perhaps we can adjust the quality of the solution that we get from the Timoshenko beam theory. So in the Timoshenko beam theory, plane sections after deformation are not perpendicular to the neutral axis. Okay, so that's the difference between the two theories. So it's a fairly, let me say, unified solution approach. You do bulk of the work in finding the rotation. And just when you're evaluating the deflection or integrating towards the deflection, there is a difference. So now let me, just to highlight, I've said several times that there is an additional contribution that always has to do with shear. We see that contribution here. And we said that this contribution is not important if the beam is really slender. In other words, the height is very small with respect to the length of the beam. So by looking at this term, we can do an order of magnitude analysis to make that more clear. And let's do that. So now first, there is this term V appearing here. But when I look here, I see that V is equal to EI times theta double prime. So I'm going to make use of that. So V is equal to EI theta double prime, which means that the derivative of the deflection is theta minus EI over kappa mu cross-sectional area theta double prime. Now, I'm just going to do an order of magnitude analysis. This is the second derivative of the rotation of the cross-section with respect to the horizontal coordinate of the beam. So I'm just going to integrate order of magnitude-wise, indicate, the rotation at the end of the beam, let's say by theta. Theta is more or less a representative rotation of the cross-section. And there is a second derivative with respect to the horizontal coordinate. Instead of that, I'm going to put length squared. So this is a quantity that sort of represents the second derivative. Of course, the second derivative changes at every point, so it's just the order of magnitude analysis. So I wrote theta over L squared. So now what we have is V prime is equal to theta minus a quantity that is hopefully a reasonable approximation. Order of magnitude-wise, it's equal to EI over K, let's put K separate, mu A L squared theta. Now, here I have several terms, of course. Now, first, let me highlight that eventually, well, actually, let's first do this. I'm going to call this quantity gamma, a capital gamma, just in order to eventually make use of it also in our solutions that we're going to obtain in an example that I'm going to solve shortly. Now, this gamma will control, sort of indicate how important the shear influences are. Now, it turns out that the argument is a purely geometrical one, and therefore this parameter should really be only I over A L squared. So this portion of this factor alone would be sufficient to judge whether shear stresses are important or not, because E over mu is something that is order of, let's say, roughly 1 anyway. So, and I'm not interested in the material property, I'm just interested in the geometry. But I'm going to, so this factor here, I'm going to contain it within gamma because eventually you'll see. If I keep it in there, then my expressions will simplify a tiny bit. So now we have gamma. So let's look at what gamma is, by the way. So for a rectangular cross-section that is of height h and thickness t, if you put area equals th and I equals 1 over 12 th cubed, what you will find is that gamma is equal to E over mu h over L squared. Okay, so now eventually when I obtain my solutions, you will see at some point that this factor gamma will appear, and this factor appears in the portion of the solution eventually that reflects influence of shear stresses. And now we see that this factor is h over L squared. So if this thing starts going towards 0, the whole factor together, because there is a square, very, very rapidly approaches 0. So as the beam becomes slender, you can very quickly ignore the influence of shear stresses. That's eventually what it will come down to. Okay? So we've seen that, I've said several times that the ratio h over L is the thing that controls the influence of shear stresses. And here in this factor, we see that ratio h over L explicitly. Okay? So let's make a note of that here. So shear influence on deflection rapidly diminishes with h over L going to 0. Okay, so that's our geometrical ratio. Okay, so now I'll keep the solution diagram up here. And I'm going to solve now the cantilevered beam problem that we attacked analytically before. I'm going to solve it now under the approximation of beam theory. So, okay, so let's revisit our problem. So I'll just draw the problem very quickly once again. So we have the vertical load, length L, cross-section as denoted. What I'm going to do is also I'm going to take a cross-section over here and indicate the free body diagram on the right. So let's use a different color. So that's the P. And by default, the internal bending moment is that direction. Internal shear force is in this direction. That's m of function of x1. So m is equal to, so this here is, the distance is now x1. So it's minus px1. And the internal shear force, it's a constant, and it's equal to minus p. Let us now solve what the deflection is for this beam. So deflection, again, it's going to be the vertical displacement along the neutral axis x2 equals 0 line. Okay. And I'm going to follow this solution diagram. So the first step is to start with the rotation. I know what the loading is. Once I find the rotation, it's common to both beam theories. I will go to deflection, and that's where the two beam theories differ. Okay, so now when I look at my problem eventually, I see that there is no distributed load. And so I could immediately start from the second step, but I'm going to start from the first step anyway, just to, for the sake of following the solution procedure. So step one is the rotation step. So I'll take EI factor to the left to simplify things a tiny bit. EI theta triple prime, that would be equal to W, but that's equal to 0. So I integrate once towards the second derivative of rotation. If I had some distributed load as a function of x1, so I would have to spend a little bit of time doing that integration, but I don't, so that's trivial. So in this case, the result is equal to V. Now, in this particular scenario, the V loading is very simple. There is no concentrated load at any position along the length of the beam. If that was the case, I could use things like, I don't know, like a Macaulay bracket, remember from ME 231, in order to sort of express this V distribution. But in this case, it's very simple. It's a constant, so it is minus P. Okay? So I don't really have to put any effort there either. So now the first real effort, well, it's not an effort, but the first serious step takes place towards theta prime. So that's equal to the moment distribution. And now I am integrating towards the moment distribution. So it's minus P x1. And of course, I could always throw in a constant. Now, I'm just doing this for the sake of completeness. Now, of course, I know that at x1 equals 0, the moment is equal to 0, and therefore, this constant is not really there. So I dropped it. Okay. Again, in general, for a more complicated loading, you have to be careful. You have to throw in your constants. You have to throw in your Macaulay brackets, whatever. So presently, it is rather simple. So then the last step, EI theta. So now I am integrating towards the rotation. So minus P over 2 x1 squared. Now I have another integration constant. Let's call that C1. The rotation describes eventually the rotation of this cross-section. Okay? Now, where the beam is attached, that cross-section is constrained from rotation. Okay? And so I'm going to say that the beam does not rotate at the point of support, which is x1 equals L. That's what we always used to do in ME231 as well. But remember, that's also what I've done in the analytical solution, not at every point, because there were too many requirements to enforce the fact that displacement was essentially constrained along the whole vertical line at x1 equals L. Instead, I just picked x2 equals 0 point, and I said that at that point, if I draw a short blue line, that line will not rotate. So its rotation theta was constrained to be 0 in the analytical solution as well. So qualitatively, what we're doing is really the same. Okay? So let's say as an exact solution, enforce theta at L equals 0, right? And for this to be 0 at L, C1 has to be equal to P over 2 L squared. Hence, we obtain our solution. Theta of x1 is equal to P over 2 EI L squared minus x1 squared. So now that we have the rotation, we're going to move on to the deflection step, and that's where we have to pursue two different approaches. Sorry, were you done writing? Yeah, okay. So I want to keep this board up here. That's why I'm going to erase this one. I have to unfortunately move this one down there. Okay. So step 2, deflection. And I'm going to start with Euler-Bernoulli theory. And Euler-Bernoulli theory states that, or proposes that, V prime is equal to directly theta. And we just found out what theta is. It's P over 2 EI L squared minus x1 squared. So now I can integrate towards V. So V is equal to P over 2 EI L squared x1 minus x1 cubed over 3 plus a constant, let's call it C2. So in the exact solution as well, we did something similar. Well, obviously, where the support is, we don't expect any deflection. And therefore, again, as in exact solution, enforce V of L to 0. Again, in the exact solution, V at L is equal to 0. The vertical displacement was enforced to be 0 in the analytical solution, I should say, not the exact, but anyway. But at any other point other than x2 equals 0, in other words, along the neutral axis, it was not necessarily 0, okay, because we had to somehow relax our constraints. Only along the center line, along the neutral axis, we enforce it to be 0. So with beam theory, that correlates very well because we're only looking at the neutral axis deformation in this case. So presently, if that is supposed to be the case, so if I plug in L, that's a 2/3 here, right? 2's cancel, so C2 is supposed to be equal to minus PL cube over 3EI. And hence, we obtain that V of x1 is equal to, let me rearrange it a little bit for future purposes. That's our solution. Okay, so here I can make two observations. So first, I can evaluate the tip deflection, which at the end of the analytical solution we call delta. So delta is simply minus V of x1 equals 0. And so we see that that's equal to PL cube over 3EI. So at this stage, it's useful to remember, if you go back to the expression for tip deflection in your analytical solution, you'll see that the tip deflection is not only this, there is another term. Okay? The first term, and it's this term actually, is what we called delta n in the analytical solution. And we said that that portion of the deflection, delta n equals this, comes from the influence of bending moments. And the second term comes from the shear force. And so here, we don't have the second term, which reflects shear force effect. And indeed, we already said that the beam theory, Euler-Bernoulli beam theory, is omitting the influence of shear stress, and it is only exact if we have a pure bending scenario. Okay? And therefore, we capture the first term exactly, but the second term is not there. The second thing that we need to recall once again is V prime is equal to theta. Okay? And therefore, V prime at x1 equals L is 0 because that's what I enforced theta to be while I was determining that free constant. Okay? And therefore, if I go ahead and try to draw how the deformation looks for the Euler-Bernoulli beam theory result, let me first draw the neutral axis. Okay, so there's a tip deflection, and the variation is cubic. Okay, so it's going to decrease towards 0 vertical displacement, 0 deflection, and the derivative of the deflection at x1 equals L is equal to 0. So the slope has to start off from 0, and it goes like this. Okay, so this here is delta. Okay, so the slope being 0 is an important feature. Unfortunately, when I was qualitatively drawing the neutral axis deformation in our analytical solution, I realized the same picture, which actually was a mistake. So now, when I talk about the Timoshenko solution, I'm going to correct that mistake. Okay, so when I was, just for the record, we are being recorded after all. So there, I said that the vertical, if I draw a line, a vertical line here, that line does not rotate. So the rotation of the line is equal to the slope of the deflection in the Euler-Bernoulli beam theory. So if this line does not rotate, then the slope here is also equal to 0. But that's not the case in the Timoshenko beam theory, and that's also intrinsically not the case in the analytical solution. And therefore, I should have been a little bit more careful. But now I'm going to correct that. OK, so this is the result for the Euler-Bernoulli theory. Let's move on to the Timoshenko beam theory. And and I hope to be able to fit everything onto the other half so we can do a comparison. The Timoshenko beam theory. Okay, so we start with V prime is not equal to theta anymore. It's equal to theta minus that. So I told you that the shear correction factor is something that we need to decide on. I didn't tell you what its value is. We're going to discuss that shortly as well. So if we look at the picture down here, the shear force is simply equal to minus P, right? And therefore, we have theta plus P over K mu A. And in fact, sorry, let us plug in what theta is so we can do the integration. So theta is equal to P over 2EI L square x1 square now plus P over K mu A. And now I'd like to integrate towards V. So V is equal to, well, the first part is the same as the Euler-Bernoulli step. So it's x1 minus x1 cubed over 3 plus P over K mu A x1 plus a constant, let's call that C2. And again, as in the exact solution, let's enforce V of L to be equal to 0. And in that case, what we're going to find out is that this constant C2 is equal to minus P L cubed over 3EI and minus PL over K mu A. Okay. And now if I go ahead and again write the final result for the deflection, let me again rearrange. I'm trying to make everything look as similar as possible. And that's the expression. Now, one thing that's nice about this expression is right here, I noticed that there's a term that I recognize to be what I defined as capital gamma, the term that sort of intrinsically reflects the influence of the slenderness or the degree of slenderness. So let's go ahead and do our comparison or calculation of major results, such as tip deflection. So delta minus V of 0, in this case, it's equal to, I'll write it in two different ways. First, we can write simply PL squared over 3EI. In fact, PL cubed over 3EI. So just 1 second. So there is a 1 over, there's a 1 there. I think I made a mistake in my notes, so let's correct that. If x1 is equal to 0, I have a L there, and I want to keep gamma over kappa here. I'd like to have a 3. No, I'm fine. I thought I made a mistake, but I'm fine. Okay. 3 gamma over k. So that's the first way I'll write it, because here we explicitly see that standardness idea is that gamma goes to 0. And as h over L goes to 0, gamma, remember, goes quadratically to 0. So therefore, this ratio will rapidly diminish, and I'll be left with PL cube over 3EI, which indeed is the solution from, right, the Euler-Bernoulli beam theory. In other words, if the beam is indeed slender, it turns out that the deformation due to shear stresses is indeed negligible. Okay? So, but if it's not, there is an additional term. Now, I'll write once again explicitly what the total deformation tip deflection is by multiplying through because I'd like to name these two terms separately as, well, the first one is our definition of delta n that appears also in the analytical solution. Now, in the analytical solution as well, we had a second term. That second term we call delta S. Again, I'm going to call it delta S here as well. This delta S and the one in the analytical solution at this stage are not necessarily the same. You will see that they're almost the same, but in general, not necessarily the same. But I'm going to call it, nevertheless, delta S to indicate that that is the contribution that has to do with influence of shear. OK, so the Timoshenko beam theory is reflecting influence of shear as in the exact solution. And moreover, as in the exact solution, the Timoshenko beam theory differs in the description of the rotation of the vertical plane and the slope of the neutral axis deformation. So V prime L is something we can evaluate here, and it is simply equal to P over K mu A. And that is not, let me highlight, equal to 0. Okay? What is 0 is theta, which describes the rotation of the vertical plane. Okay? That is equal to 0. But V prime is not equal to 0. So which means that eventually when I draw the same picture here once again, so I'm going to draw not the same picture, but if I want to describe the deflection graphically, so this is the neutral axis. Okay. And now, again, we have our tip deflection. And the difference is now the slope of the deflection curve at x1 equals L is not 0 anymore. It's at a certain angle. Let's draw its continuation like this. It's hard to draw a very good figure here. Let me just try once again. Something like this. So this angle here, it is equal to beta. Right? That's what we called it when we were developing the theory. And beta is not equal to theta. It's equal to this. So this is beta in this case. at x1 equals L, and P is positive, everything is positive, so this is positive, which means the slope here is positive. And the tip deflection is delta. Okay. So even qualitatively, there is a difference. Now, eventually, I will try to show you with a numerical solution. This slope is not so prominent. So it's not 0, but eventually when I solve, you'll see that it's hard to see it. When we zoom in, we will see it. But it's really not extremely visible. I have truly exaggerated here. So now, I want to remind you also what the exact solution was, or the analytical solution. I keep saying exact, so that refers to the analytical solution. Exact within our approximations of the plane stress of the plane stress setting. And the solution qualitatively is, again, going to be depicted like that. But let me just write down the analytical results. So now I can erase all of this, right? Because I've applied the process to both beam solutions. There still remains K to be determined. I don't know what K is yet. The shear correction factor is something I still need to find out. And that's partially why I am going to write down the analytical solution. So let's call that exact. So what I'm doing is I'm writing down the deflection, which is U2 evaluated along x1 at x2 equals 0. That's our definition of deflection. And when you do this evaluation in your analytical solution, you had to do a little bit of rearranging to get this expression. But you essentially have the result already in your notes. So let me do the rearranging for you. And I am writing it in as suggestive a form as possible, so we can do a comparison with the right-hand side. So I'll write down the tip deflection as well. That is the tip deflection. And again, I will evaluate V prime at L from that expression. It's going to be equal to P over 4 over 3 mu A. Again, that's not equal to 0. Now, when we were developing the analytical solution, what was 0 was a rotation. And that rotation, however, unlike the beam theories, it's not just a function of x1. It's a function of x1 and x2. However, enforcing rotation to 0 at every point along x2 at x1 equals L was simply not possible. And therefore, we relaxed that condition, and we picked only one point, x2 equals 0. Okay? So that was 0. This rotation was 0. But V prime is not equal to 0. It's positive, actually. Right? So now, can we get a special shot here that somehow tries to show this portion at least of the boards, because I'll now try to wiggle back and forth, oscillate back and forth between those two boards. So now what we have is on the board the analytical solution, Euler-Bernoulli, and the Timoshenko beam theory. And so first of all, now you can go look at your notes. This is what we defined as delta n. This is what we defined as delta s. So now I am re-expressing those results by introducing the constant gamma as well. So, but quantity-wise, they're exactly the same. Okay? And at that time, I had said, well, there's a second term. That term diminishes with h over L going to 0. Now we see it, because now I have this factor that I discussed, gamma. And I had said that, well, that term has to do with the influence of shear stresses. Now we understand why. But now what we can also do is we can compare our solution with the Timoshenko beam theory. And we see something remarkable, actually. So in the Timoshenko beam theory, if I go ahead and choose k equals, right, 4 over 3, the tip deflections match perfectly, right? They match perfectly. Not only do the tip deflections, it's the whole deflection matching perfectly, right? So this is gamma over k, x1 minus L, gamma over 4 over 3. So k equals 4 over 3 allows Ti to match the exact solution or analytical solution in deflection. The deflection matches, the slope matches, therefore, and in particular, as a result, the diagram for deflection curve is exactly like this. If k equals 4 over 3, then it's exactly the same as the diagram for the Timoshenko theory. Okay? So that's quite remarkable. Okay? Now, remember, these are approximate theories. In particular, this is omitting shear stress. This is saying, well, I have constant shear stresses. The analytical solution is not doing that. So as a result, it is not only able to say something very reasonable about what happens away from the neutral axis, on the neutral axis, but also away from the neutral axis, whereas these are accurate on the neutral axis. So away from the neutral axis, it's a vague world. But nevertheless, on the neutral axis, Timoshenko beam theory is able to match if you do a judicious choice of k, which is screaming at us, choose me 4 over 3. So you might think that, well, okay, so the single reasonable choice here seems to be 4 over 3. It seems not, okay? So this is a homework problem. You're going to work on it. So there is also the energy aspect. So in other words, if I take a force, right, I'm applying a vertical force P, and this thing deflects by a certain amount, and this deflection does a certain amount of work. There is a certain amount of energy stored in the beam. Internal energy is equal to external energy input. And you can go through that analysis, and eventually what you would like to have as an alternative scenario is that the energy that is stored in the beam after bending matches the energy of the beam in the analytical solution. That's an alternative picture. Now, it turns out that picture does not deliver the same value of k. In other words, if you want to match the energies, you will find in the homework problem that you have to choose k equals 5 over 6. Now, the deflection has two parts. There is a bending part and there is a shear part, bending moment and shear. Bending has to do with normal stresses, shear with shear stresses. And because we're doing isotropic linear elasticity, the energy eventually can be decomposed into a part due to normal stresses and part due to shear stresses. Because the normal parts match in their formation, it turns out the beam theory already matches the energy due to bending stresses exactly. The one that doesn't match is the one due to shear stresses. So when I say match the energies, really I'm talking about trying to match the shear strain energies. You're going to go over this in detail in the homework. Okay? So when you try to match the energies, you have only one constant to adjust, and it's K. And it turns out it has to be 5/6. Okay? So, but it's one or the other. There is no, it's either that picture or that picture. It turns out that this is a more common picture because it is more reasonable for most people to think that you are capturing the exact energy. Okay? Deformation, it will be nice to get, but energy is usually of higher importance. All right, but I suppose it depends on the application. So that pretty much completes our beam theory discussion. Okay? So now what I'd like to do in closing is just put all of this together and demonstrate to you how this all compares against the numerical solution. So I have sort of already, unfortunately, said that exact represents analytical, but in a sense, exact is going to be now represented by our numerical solution, provided, of course, the numerical solution is accurate enough. Okay? So the analytical solution is exact under the given assumptions. So that's why, at that time, I called it exact. Okay? On that board, for instance. Okay, so this is how we're going to carry out the comparison. Now, what I have here is the geometry that eventually we would like to simulate. So we know that there are eventually end effects, and so I'm going to apply a force here on the left and keep this end fixed as in our diagrams all the time. So after deformation, right, that's the solution. We see that, so what we're looking at here is sigma 2,2, which within our approximate solution, well, within our analytical solution, by omitting the end effects, we found out to be 0. Okay? Now, they are not 0. Okay? And in fact, they are about, let's say, 1 order of magnitude less than sigma 1,1. So it's not really negligible at the ends. But you see that they are limited to a very small region, and end effects always have to do with h. And we expect some exponential decay, and they rapidly diminish inside there in the 0. This is eventually the picture that I'd like to go. The higher I make the beam, the end effects will dominate. I expect a significant deviation of my analytical solution from the numerical solution, which is able to solve, in any case, quite accurately what the distributions are like. So although this is my goal, let me first, therefore, take the step where I really actually have a large height. Okay, so here I've defined, again, many parameters. And let me go ahead and first modify the height to 0.6. So 0.6, the length is 1. Okay, so the ratio is pretty high. And let's go ahead and compute. Okay, so now have a look at the number. 4 times 10 to the minus 4. I mean, like almost 1/4 overall of the domain is dominated by these end effects. So they should really be influencing the solution in the middle as well eventually. So analytical solution should not be an excellent match at all, actually. But so let's look at the magnitude of these stresses, 10 to the minus 4 times 4. If I go ahead and look at the x stress, sigma 1,1, okay, 4 times 10 to the minus 4 versus 2 times 10 to the minus 3. So it's like even larger than a factor of, let's say, a factor of 4. Okay, so 4 to 5, let's say. So the sigma 2,2 is not really negligible, right? They are significant. So how does that eventually influence the comparison of analytical versus numerical? And also, we can throw in the solutions from beam theory where they're applicable. So let's have a look at, so what I'm going to do is several things. One, I will show you deflection curve. Deflection curve is taken along the neutral axis, x2 equals 0 before deformation. And also what I'm going to do is I'm going to look at the stress distribution as well as the horizontal displacement, U1 distribution, when I take a horizontal cut. Okay? So at a given x value. So I'm going to show you now several one-dimensional examples, one-dimensional curves, and first the normal stress. Now, remarkably enough, when you first look at the normal stress, you see, so numerical versus analytical, despite such a strong influence of end effects, there is almost a perfect match. Numerical analytical solution predicts my over I. So linear variation with respect to y. Here, this is the y coordinate. This is the magnitude, the value of the of sigma 1, 1, right? So 0, negative, positive. If we are below x2 equals 0, so we are below the neutral axis, it is compression, right? And on the neutral axis, it's 0. And above the neutral axis, it starts to become positive and it's linear, exactly as in analytical solution, or analytical solution exactly as in numerical solution. So, but here, the cross section I have taken is right in the middle of the beam, where end effects were almost not seen. Okay? So I will choose another cross section and actually show you that eventually the match is not always perfect. But we can already go to, for instance, the shear stresses. Now, notice that here I'm only comparing numerical versus analytical. Shear stresses are something that is not captured in the beam theories at all. So only numerical and analytical. The match is almost perfect again. So it's VQ over IT. Q has a parabolic variation. So parabolic variation 0. So this is the magnitude, the value of the shear stress. It is positive. It has to be. Above, it's positive. Below, it's positive. At the top of the beam, it's 0, right? At the bottom, it's 0, and it is a maximum on the neutral axis, okay? Just as we remember also from ME 231. And if you zoom in, there's a small mismatch, and that's because we don't expect an excellent mismatch anyway. Eventually, of course, there are still end effects. It's a very, H over L ratio is very high, so such an end effect is expected. I was surprised by the good match of the bending stresses, but they don't have to match very well anyway. So this is expected. Still, it's an excellent match. Now, I can look at a given cross-section, the value of, or the distribution of U1. This is U1, right? So what this means is negative, positive, above, below. So above the neutral axis, so I'm bending, right? So the cross-sections rotate like this. And that's what you're seeing. It's rotating. Blue is numerical, red is analytical, green is beam theory. So beam theory is a straight line. Cross-sections remain plane. Blue is numerical. It's deviating from the green, which means plane sections do not remain plane, which I already know from my analytical solution. And that is the analytical solution. It's also not a straight line. So plane sections do not remain plane. And here, the influence is important because eventually the deviation from linearness is what gives you the correct transverse shear stress. So you might be a little bit disappointed by the fact that the red line, which is analytical, seems to be far from blue compared to green. But green is straight, gives you turbo shear stresses. Okay? Whereas the red line gives you the good transverse shear stress match that I have already shown. So deflection-wise, it's not very good, but shear stress-wise, it's very good. Again, I don't expect a very good match in deflections anyway. The height is currently very high. There are end effects, so it will dominate, perhaps, features of the solution. Let's look at deflection, on the other hand. So blue is the numerical solution. The analytical solution is much closer to blue than the Euler-Bernoulli beam theory solution. So now, let me go back. I'm sorry for doing this, but this is U1. U1 is minus theta x2. That's how it was represented. And theta is the same for Euler-Bernoulli or Timoshenko beam theory. So here, when I have drawn a line, I've only indicated beam theory because rotation is described in the same way for both theories. Now, when I look at deflection, however, there are two different theories. There is Euler-Bernoulli, which doesn't take into account the influence of shear stress, and there's Timoshenko. And moreover, in Timoshenko, if I choose k equals 4 over 3, and that's what I've done here, I know that I match the analytical solution perfectly. Okay? And therefore, I am not showing the analytical solution. It's the same as the red line. Okay? So red line is equal to Timoshenko, k equals 4 over 3, is better or closer to numerical than Euler-Bernoulli. Okay? So now, not too bad, but remember, H over L is very high. So now what I'd like to do is, before I decrease it towards hopefully a better match, I'm going to go and I'm going to choose a cross-section. So I took a cross-section along the length of the beam. Right, at x1 equals 0.5. So now I'm going to take two different cross-sections. I'm going to look at this cross-section at 0.9 and then this cross-section at 0.1. These are the end effects. Why? Because x equals 0.9 is where, in the analytical solution, I was not able to enforce displacement to 0 at every point. I had to pick one point, and I picked, to relax, that was one choice, I picked x2 equals 0. So therefore, I expect some end effects here. And here, this is also an end effect. Why? Because in the analytical solution, I only represented the stresses in a statically equivalent manner. I said that when I integrate the stresses, they should be equivalent to, statically, just a vertical force. Of course, locally, the stresses will depend on how I distribute that or represent that force. But statically, in a sort of, let's say, the Saint-Venant principle manner, whatever the particular distribution is will only be an end effect, and it will rapidly diminish as I move away from that end. So presently, the numerical solution takes a constant shear stress distribution such that it integrates to a net force, a given force. Okay, so shear stress is a constant along this end. I know that my shear stress here, for instance, is VQ over IT. It's parabolic, so it will be a mismatch. It will introduce an end effect. So let's look at those. So first, instead of 0.5, I'm going to choose 0.9. And now, normal stresses. So you see that analytical is a straight line, minus mx2 or my over I. Blue is numerical, so it's now deviating from analytical. You may say it's not too bad, but let's remember that for x1 equals 0.1 from the other cross-section that I will take. Let's take a look at shear stresses. It's terrible. Okay? The analytical solution VQ over IT, but now end effects start to dominate, and it's entirely different, right? Again, these are expected. I'm just showing you the limitations of our analytical solution. You can also look at the X displacement again. It's not very good. But let's concentrate on the stresses. Normal stress, not too bad. Shear stress, pretty bad. Now I will go to the cross-section. x1 equals 0.1. Now, the normal stresses are terrible, okay? Because the normal stresses eventually in the numerical solution, they have to be 0. The left end of the beam, it is traction-free in the normal direction. I'm not imposing anything in the numerical solution. So the numerical solution will try to decay to 0, but the analytical one is always my over I. It also goes to 0, but because the bending moment is going to 0 there. But it always remains as a line. In the mean, of course, they are statically equivalent, right? So the integral of the blue line causes a certain moment that is equal to the moment due to the red line, right? But the mismatch is quite significant. On the other hand, if you look at the shear stresses, it's not as bad as, for instance, x1 equals 0.9. So, but in any case, we observe the end effects, right? So, and all of that is because the height of the beam is significant. Now, what I'm going to do is I'm going to keep the cross-section fixed at x1 equals 0.1, very near the end, but I'm going to decrease h. Not too much, actually. I'm just going to decrease it to 0.2. So 0.2, h over L is 0.2 squared, 0.04. Like 4% end effect influence, let's say, waving our hands. So it shouldn't be too large. 0.2 is not a small number, but h over L squared is a small number. So let's do the solution. Okay, so this is the picture I showed you at the beginning. And if I look at the normal stresses, I'm at x1 equals 0.1. There is a very, very good agreement compared to the previous picture. I'm close to the end. If I move away from it, very rapidly, the lines will almost match. If I look at the shear stresses,
a very good match. Okay? Let me go ahead at this point and actually do choose a different point, let's say point 5, and update these plots. Perfect match of normal stresses, almost perfect. Very, very good match of shear stresses. If you look at displacement, very good match of displacements. And if you look at deflection, Timoshenko versus beam theory, right? It's a very close match, better than Euler-Bernoulli. Okay? So now, here the height is already very small, but if I eventually zoom in a lot, okay, and this is as much as I can do. Okay, so perhaps this is not the very good way to go. Let's choose the height to be 0.6. I'll compute once again, but because it's not very clear. Okay, quick deflection view. Okay, so now I'm zooming into the end. Green is Euler-Bernoulli. The slope of the deflection curve is going to 0, right? And this is what I wanted to show you. Timoshenko beam theory and the numerical ones, on the other hand, have a non-vanishing derivative. Okay? The rotation that we're describing is the rotation of that line. So this thing can have a non-zero slope. Okay? And of course, on the other hand, as a final check, when we talk about beam theory, what we're really willing to talk about, perhaps, is something that looks like this. Something that is even thinner. Okay? So this is a better, let's say, deflections, by the way, here they are magnified by 10. So in reality, it's less, small deformation, relatively small rotation. Okay? So this here is a case where we have really almost, for all practical purposes, excellent match of shear stresses, normal stresses, X displacement, deflection, etc. In fact, even the beam theories are doing very well because indeed it's so slender that the match is excellent. It's expected to be excellent. Okay. So that concludes our lecture on beam theories. And we have a few lectures left. And the most important outstanding problem that stands out presently has to do with actually, again, a fundamental problem, as in this ME231 problem, but not bending. This time it's going to be torsion, but torsion of non-circular cross-section. So that's our next goal. Okay, so thank you.